Okay, here's part two about the UMP test finding using Neyman-Pearson lemma. Now we're going to extend this to the case we're used to, the composite alternative hypothesis. When, I don't know if I mentioned this in the last lecture, but when you are testing a single parameter equal to something and everything else is specified in your distribution, it's called a simple hypothesis because it completely specifies the distribution. A composite hypothesis doesn't completely specify it. So over here, now we have shifted over to a composite alternative hypothesis. The null hypothesis is still simple. We know what it is exactly. But the alternative is now the typical case we've been seeing. It's a composite hypothesis. In other words, for any mu greater than mu zero, we have a different distribution. So we don't know exactly what the distribution is. It still depends on exactly what that is. Okay, so you'll see we get lucky here. So I'm not going to attempt to guess actually where they thought of this, but I can kind of imagine that that they found this out in a similar way just by doing these computations and seeing what we're about to see. So okay, so we have n samples. We're going to model them as normal mu sigma squared with sigma squared known, and we're going to test mu is equal to some mu zero versus mu is greater than that at alpha equal 0.05, just could be any number, but just to keep it concrete. And the question is, can we find a UMP test? Well, what do you think it means now? So the meaning now has shifted because it's not clear what the HA is saying exactly. But what this really means is that it doesn't matter. Like no matter what mu is bigger than mu zero, this test should return the most powerful version that has all this other stuff, right? So bounds alpha at 0.05 and has this distribution, everything else the same. So it should work. It should have the lowest type 2 error at, slightly bigger than mu zero all the way out to huge values, okay? All right. So let's see what happens here. So the trick is just to to make it a simple hypothesis and then see that it didn't matter what we picked. We still get the same rejection region. Okay, so this is the key trick. So let's write solution. So let mu A be just some arbitrary number greater than mu zero. You can write the word arbitrary if you want to make it clear, but you don't have to. Okay, so I just pick some number bigger than mu zero. And we consider the test and consider the UMP, finding the UMP for H0 mu equals mu zero versus HA mu equals mu A at alpha. Okay, then NP says RR will give me the UMP test if it's equal to this L Y. I'm not going to write the sigma because it's known. Mu zero L Y mu A. Sigma is known. Come on, go away. Why are you doing that? And this is equal to. So this is the test. This is equal to Can I write it all out here, fit it all in? Yeah, let's write it down here, equals 2 pi. Little silly to write it. We know it's the same on the top and the bottom, right? And this should be less than k, right? Less than k. So let's give a little room. This is my rejection region. Okay. And what else do I have? I have exp on the top, sum yi minus mu 0 squared. And on the bottom, same thing, exp minus 1 over 2 sigma squared, sum yi minus mu a squared, less than k, right? Well, a lot of nice cancellation. So this is also equal to, so this is equal to this is less than this. I will simplify now and have a single exponential. So I have exp. Let's take the minus 1 over 2 sigma squared out front. And then I have the numerator minus the denominator, right? So I have sum close that, close this, less than k. Right? Yes. All I did was some algebra there and just clean that up. Okay. Well, let's take the logarithms, right? That makes sense. Just we're going to just keep trying to make it more simple. If I take the logarithm and let's do a couple steps and multiply by minus 2 sigma squared on each side, we get this is the same as now. Log you can take and keep the inequality the same, but multiplying by minus 1 over 2 sigma squared will flip the inequality. So we get, finally, we get sum yi minus mu 0 squared minus sum yi minus mu a squared has to be greater than minus 2 sigma squared ln of k. Okay. Yes. Okay. Okay. Looks fine. I think the next thing to do is to clean this up a little bit. So one thing you can see, the yi squared will go away here. This is good because it will reduce this down to a single y. We can find a single statistic here by doing this. So let me just write this in here. Let's give it a little color or something maybe. So we write this in here like kind of too light looking. But yeah, so I get 3 terms on the left, 3 terms on the right. The yi squareds will cancel, right? So I should have 4 terms. So this becomes, and let's apply the sum too. So I get minus 2 mu 0 y bar here. And an n, right? Minus 2n mu 0 y bar, right? And then I have plus mu 0 squared, right? And then n of those, plus n mu 0 squared. Over here, I get a similar deal, but I am subtracting, so I get a plus 2n I don't like this color. 2n mu a y bar, and I get a minus n mu a squared, right? So that's what that is. And you can see we can collect those, and we want to isolate the y bar, right? That's going to be our test statistic, is the sample mean. Let's go back to the black color, or I just would have liked a darker green. Okay, so what do we have? Let's see, how can I clean this up? I want to just isolate the y bar. So maybe I would, yeah. So let's just go to this now. I have, I don't want to do too much at once. Let's see. Let's write this like this. 2n mu a minus mu 0 y bar. Keep this over here. And this has to be greater than this side. And then I am going to get rid of this stuff too, right? I'm going to add it. So this has to be greater than minus 2 sigma squared ln k. Okay, and then what happens? I'm adding n mu a squared, and I'm subtracting n mu 0 squared. So I get plus n mu a squared minus mu 0 squared. Okay. That looks right. Right? I want to divide by 2n. And why not divide by mu a minus mu 0 while I am at it? So we get equals y bar. Notice this is the same rejection region we started with, is greater than. And look, I can see I can divide out some of this stuff, but there's no reason to do it right yet. Maybe at all ever. Let's just keep going and see where we get. Minus 2 sigma squared ln k plus n mu a squared minus mu 0 squared all over 2n mu a minus mu 0. Okay. Now, what do you notice? What do we want to do? We want to replace this right-hand side with k prime, right? And just claim that we can find a k such that we can set this to be whatever we need it to be. If you think about it, mu a is bigger than mu 0, right? So this is positive, and this is positive. So this this will be positive or negative, right? And so I basically have two positive numbers here, and I want to be able to claim that I can find k that will put this where I need it to satisfy the probability of type 1 error. I don't want to, I may be making this more confusing than I need to right now. So let's just see what happens next. So we're fixing alpha, right? We're fixing alpha. First of all, we've fixed alpha already. We've said it's 0.05, right? And we want to find, we want to be able to set this to ensure that alpha is 0.05, right? So let's call this k prime for now. We'll go back and look and see that this is okay to do. Okay, so the probability that y bar is greater than k prime we want this to equal, given, here, let me even make it a little more clear. Sorry, I'm fumbling a little bit on this, but I think we're almost there. So probability y bar is greater than k prime, given h0 is true. So given h0 is true. So given h0 true is just equal to the probability y bar is greater than k prime, where y bar is normal, mean mu 0, and variance sigma squared known over n, right? So this is the probability I reject, but this sample does have the mean mu 0. So this is equal to, let's standardize the probability that y bar minus mu 0 over sigma over square root of n is greater than, again, doesn't really matter, right? K prime minus mu 0 over sigma over square root of n. Okay. And we want this to be 0.05. So we need to set this equal to Q norm 0.95, right? We want to set it equal to the 95th quantile of the standard normal. And we have our test, basically. This is it. But we do have to go back and address this step, I think, but we are here. So this is equal to the probability. So this is equal to 0.05. So set the right-hand side here equal to 0.05. Okay. Okay, so I just paused it for a second just to think about this for a second. So we know that to achieve the alpha level, we want if we call this k prime, we know that we want probability y bar greater than k prime given h0 true to be 0.05. So we want the probability y bar greater than k prime to equal 0.05 when h0 is true or when y bar has this distribution. And then we can standardize and say that's the probability y bar minus mu 0 over sigma over square root of n is greater than k prime, also altered, but we want this equal to Q norm 0.95 to be right anyway. So we want this to equal 0.05. This will make this equal 0.05. So we set, right? So we set, it really doesn't matter. I could just actually I could stop here, actually. Let's look at this carefully. We could stop here. So there's two things we could do. We could set the RR based on this Z type of variable here. So you could have RR then is equal to just a different test statistic, right? Y bar minus mu 0 from your null hypothesis. Sigma's known, N is known, and here you can have Q norm 0.95, which is 1.645 or something. Or if you like, you're more a purist and you just want the test statistic alone, you could say or RR equals, and then just make it Y bar greater than, and just have it be 1.645 multiply through sigma over root n plus mu 0. This makes you, I think, a little easier to see that you want it this much bigger than the null hypothesis. One thing I got stuck here a little because I was back here and I wanted to just you to see that it's okay to throw this all away, because it does seem a little crazy to just replace this with a single letter, but it's true, right? The log of k can be any number, positive or negative. And so you're just adding something to it. So the numerator can still be any number. The bottom is just some positive number. So the whole thing scales all of any number. So this could be any number dependent on k. In other words, the range of this function in terms of k are the real numbers. So this is fine. So what do we notice? Here's the rejection region. And what can you tell me you notice about the rejection region? There's no mu a in it, right? So it doesn't depend on mu a at all. So since all it depended on was that it was bigger than mu zero. So since RR only depends on mu a greater than mu zero and not on its particular value, exact value, this is the UMP test, universally most powerful test, for every mu a in the alternative hypothesis, greater than mu zero. So no matter what, so then we can use it for the, so this is the UMP or the test for the non-simple test given. Okay, so, and it doesn't matter what mu a is. So we could use this. It's the okay. So the mu a was arbitrary. It could be any mu a. So so we can just use this test for this case. Okay, I have one little numeric example to do for this, and then that will do it for part 2 of the lecture too. So so like a little example. Let's just do a little baby example here. So example, suppose we have y1 to y16, just to see some numbers, normal mu, say 10 squared, and say h0 is mu equals 75 versus HA mu greater than 75, and you want to test at level alpha. Okay, solution, we just did it. So you don't need to reinvent the wheel. Rejection region is equal to y bar greater than I don't remember what it was. Q norm, right? Yeah. Q norm 1.645. There, did we have it here? Let's just see. Yeah. 1.645. So Q norm 0.95 times sigma over the square root of n. So sigma is did we give it here? Sigma is, oh yeah, sorry, sigma's 10, right? And n is 16, so it's going to be 10 over 4, so 5/2, and plus mu 0, which is 75. And if we do that, we get 79.125. Okay, so with 16 samples and the standard deviation of 10 for each sample, of course, the standard deviation is only 2.5 for the mean, right? We would only incur a type 1 error with probability at most 0.05 or exactly 0.05 with this test. In other words, if the average of 16 of these normals exceeds 79.125, we will reject H0, that mu is 75, in favor of the hypothesis that it's bigger than 75. So I need to reach 79 and 1/8, and then I am comfortable with that. Also, at this point, I can compute a power function for all mu greater than mu 0. I know at mu 0, it will be at 75 here, if we try to go power of mu. I know it here, it will be 0.05 down here, right? But it will increase as I move away from here. Okay. And I'm not actually sure it looks like this. I didn't do it yet. But this will be something we will do for this. Okay. So let me write that. Okay. But anyway, this is the best. This is best of any alpha 0.05 test for these hypotheses and sampled. Okay. We'll see you next time. That's it for UMP tests and Neyman-Pearson lemma. Next, we'll do likelihood ratio test.